So last time we were explaining the stress strain curve in compression, and we said that we have mainly difference between stress strain curve in compression behavior and tension behavior for the engineering curve, while for the true curve we can detect several common aspects. Okay, so to start with, we will repeat the explanation for the behavior in the engineering curve. So already we can detect an elastic region where the engineering stress is varying with, and as I told you, when you present positive value, you put just compression to say that it's a compression test. Or you can just remove C and put a negative value. Okay, so this is function of epsilon engineering compression. So if we want to explain the physics here, the linear part corresponds to the elastic region, and we can detect the yield point, which is a transition between elastic and plastic. Here also we can use the offset method if this point is not very clear. Now in the first part, the behavior is similar to the case of tension. So you have reduction in slope, because as you go from elastic to plastic region, it will be easier to deform your specimen. Okay, and you will have you need to still increase the force, but the rate of increase will be reduced because it's easier to deform in the plastic region. However, at a certain point, this behavior will stop, and you will start to see an increase in the slope of variation of the engineering stress, which is proportional to the force applied. What is the reason for this? Because there is something particular happening in compression test, which will contribute to the increase in the stress and at a higher rate. In fact, as the cylindrical specimen is squeezed, friction at the surfaces in contact with the plates will tend to prevent the ends of the cylinder from spreading. So we were talking about this last time. If you consider as a case of compression test, so what will happen is that you are squeezing a specimen between two ends. And here, where you have contact between the end plates and the cylinder, at this level, you will have development of friction forces that will oppose increase in area at this level. You know that during compression, the area of your the cross-sectional area will increase as you proceed with the test. Okay, but here there is development because of friction between the specimen and the plates which are in contact. These friction forces will tend to oppose this behavior at the end of the specimen. Okay, and with as you proceed with the test, these forces will increase, and at a certain stage they will become very large, so that they will lead to the need for higher forces and at a higher rate to continue the compression test. Okay, so in this case, additional energy will be consumed by this friction during this test. This will result in higher applied forces, which explains the increase in rate. It also shows up as an increase in the computed engineering stress. Hence, due to the increase of the cross-sectional area and friction between the specimen and the plates, the characteristic engineering stress strain curve obtained in compression will be different than the one obtained in tension. Okay. Now, another consequence of the friction between the surfaces is that the material near the middle of the specimen will be permitted to increase much more than at the ends. Okay, so you will have what we call the barreling effect. So when you reach a large stage of deformation, you will see this profile at the end. Okay, you will see that you will not have at a certain stage here when you go through the zone. No, you will not have any more, if you want a nearly uniform distribution of area. You will have at the ends like the area is smaller, while in the middle it's larger. And if for considerably large value of epsilon, this will lead to certain deformation. So this is why in case of compression, we say that one of the failure mode is that we reach a deformation state that is very important, and we consider that this can be defined, a certain stage of barreling can be defined as the limit of the compression test. Okay. Now in compression, we have several modes of failure. We said that in case of tensile test, the failure mode is mainly because of necking. So you start to have necking, and at the end you will have fracture of your specimen. Okay. Now, in case of tension, compression failure can be defined in several ways depending on the material. And sometimes you can have collapse or buckling of fibers, which will result from the compression test, which will lead to failure. So this point can be defined in several ways. Or when you have collapse or buckling of fibers, other materials will fracture at their compressive strength limit if they deform irreversibly, and you reach a very large deformation state, so that you consider that I will not proceed anymore with the compression test. So then we can define a certain amount of deformation that can be considered the limit of the compressive load. For other materials, the nature of the principal failure mode can change from axial splitting. So you might observe splitting of axis of your specimen, or you can observe shearing along a single plane. In other materials, you can observe multiple fracturing in the case within the material. Okay, so you have a lot of sources that can lead to limit of the compression test. Okay. Now, what is nice, as we said before, that for the true curves, we have a lot of similarities, not like the engineering curve. So although differences exist between engineering stress-strain curves in tension and compression, the true stress-strain relationships are nearly identical. Okay, so this is why we can profit from this to not repeat the tests. Sometimes, especially for ductile materials, we have observed that tensile and compression tests are in true curves are very similar. This is why we can extrapolate tensile test results to be used to compression test results. So we can say that the result of flow curve values for K and N from tensile test can also be applied to compression operations. And when using tensile K and N data for compression, we should ignore necking. And the difference is that we'll not observe necking in case of compression, but K and N values can be considered as common. So whenever you have a ductile material and you do the calculation of K and N, you can consider that these values are also valid for the compression test. Now, of course, this is not the case for brittle materials, because already we know that brittle materials will not go even to the plastic region. They will undergo, until tensile tests, they will undergo failure before reaching the plastic zone, while brittle materials can sustain compression. So in this case, you cannot extrapolate result of tension test, tensile test to compression test. Okay. So in this case, also the testing of these materials is not very simple. Okay, so even when you want to test their behavior in compression, conventional testing is not used. We have other type of tests. So for hard brittle materials which possess elastic but little or no plasticity, the conventional tensile test cannot be easily applied. We replace it in general by a bending test, also called the flexure test. In this case, we'll explain how bending can give idea about tensile properties. You know that when you do bending of a structure, you have seen this in statics. When you do bending, the upper part will undergo compressive stresses, while the lower part will undergo tensile stresses. Okay. And then in this case, we can consider that fracture will occur when the tension limit is exceeded for the bottom fibers. Okay, so we can detect failure in this case using bending, because the tensile test will not is not easy to apply for brittle material. Okay, so in this case, specimen of rectangular cross section is positioned between two supports, and a load is applied at the center. We can see here how we do this. So as we said, as we apply bending of the cross section, this will result in both compressive stresses and strains at the upper part and tensile stresses and strain at the lower part. Now, because a brittle material can sustain compression more than tension, so failure will be due to tensile stresses at this level. And the mode of failure will be seen here in next slides. So brittle materials do not flex. They will deform elastically until fracture. And in this case, failure occurs because tensile strengths of outer fiber of specimen are exceeded. Now, concerning the failure type, it's called cleavage. And in this type, which is common with ceramics and metals at low temperature, what will happen is that separation rather than slip will occur along certain crystallographic planes, which are close to the bottom part. So if you do observation, you will see separation along some planes at a certain level when you reach the maximum tension stresses possible. Now, another important properties of material is the ability of the material to sustain shear. So we have already seen tests used to test the ability to sustain tension, the ability to sustain compression. Also, shear stresses are important, and they can be faced in several applications and in several manufacturing processes. So we need to know the ability of a material to sustain shear. This will consist on application of stresses in opposite directions on either side of a thin element. So you can see here, for example, we take an element, we apply opposite forces. So this will lead to development of shear stresses within the material. So if you do a cut at any level, you will detect shear forces developed, and this will lead to a certain deformation. And in shear, we have a change in angles. Okay, so we can define deformation as the change in angle. So for example, if we can consider this angle alpha, since the formation is relatively small, we can say that tangent of alpha is nearly equal to alpha, because alpha is relatively close to 0. And it can be defined as delta, which is the deformation here, over the thickness of the element, which is B. Okay, so measurement of delta can give us an idea about the deformation shear, or we call it also the shear strength. So here we defined in shear stress, as we did for tension and compression, we define shear strain and shear stress. So the shear stress is defined as the force applied over the cross-sectional area. Now, what is different another difference between shear tests and tension and compression is that in shear you don't have change in the cross-sectional area. So the cross-sectional area will not vary, but you will have a deformation in angles. So what will happen is that you don't have in shear stresses two curves. You don't have engineering and true curves, because the area will not change. Okay, so here we just represent one curve, the shear stress strain curve, and the shear strain is defined using delta, as we said. So it's equal, if you want, to the angle of deformation alpha, and it's equal to delta over B. So delta will represent the deflection element that we have seen in the figure above. So this is delta, the deviation from the initial position. Okay, and B is the distance over which this deflection occurs. And this will allow us to define the shear strain. Now, concerning the curve, okay, so this is a typical shear stress strain curve from a torsion test. So we perform a torsion test to test how shear is taking place. Okay, so we have a specimen and we apply torsion on it. If you have taken mechanics of materials, of course, you have considered this. Okay, so under the effect of the torsion test, you will have development of shear stresses within your sections, and you will be able then to measure shear stress versus shear strain. Now, this is the profile you obtain, okay? We can also detect an elastic region where the variation of shear stress with respect to shear strain is linear. You can also detect a yield point, which is a transition point between elastic and plastic. Now, in the plastic region, because when we move from elastic to plastic, it will be easier to deform, you will observe a decrease in the slope of increase of the shear stress with respect to the shear strain until fracture. So in shear, there is no necking, there is no, you just have an increase of the force applied until the fracture point, which will define the shear strength. Okay, so this is the one of the easiest profiles, the shear stress strain curve. Okay. Now, we can also sometimes relate this modulus, which is called shear modulus, to the elasticity modulus. So there are some connections between shear properties and tensile properties, and we'll see this in the coming slides. So we said that in shear, we can detect an elastic region, and this elastic region is driven by the following equation. The shear stress is equal to the shear modulus times the shear strain. Now, as we said, we developed experimentally a relation between the shear modulus and the modulus of elasticity. For most of materials, we can say that the shear modulus is equal to 0.4 times the elastic modulus. So in this way, tensile test can help us into getting properties about shear. So we can determine the elastic behavior in shear from the elastic behavior in tension, and the opposite is true also. Now, in addition, we can also relate the shear strengths from the tensile strengths, okay, which represents the maximum value of shear related to the maximum shear strengths related to the maximum value in tension. So the shear strengths for also, we have experimentally developed a relation between both. So the shear strength is nearly 70% of the tensile strengths. So in this case, if we conduct only tensile test, we can deduce some properties of shear stress versus strain behavior. Now, since the cross-sectional area of the test specimen in torsion does not change, as we mentioned before, then engineering stress strain curve is nearly the same as true stress strain curve. This is why in shear, we don't talk about engineering and true curves. We just represent the shear stress function of the shear strain. Any question? Please stop me if you have any question, okay?
دكتور بالسلايد اللي قبل كان decrease in slope لأنه less force is needed صح؟
No, look, مش less force is needed. بضل بدك تزيد الفورس, okay? بس the rate of increase of the force is lower. يعني look, the shear is always increasing as you progress. Okay, so you will always need to increase your force because the shear is force over area. Okay, and since the area is constant, then the variation of shear will represent the variation of the force applied. Okay, so as you can see, the increase is continuous, but the rate of this increase is variable. So you still need the highest force applied will be here at fracture, but what differs the elastic from plastic region is the slope of variation of this force with strain. So we say that because it's easier to deform then the rate of increase, I don't have to increase a lot the force to cause a certain deformation. So as I go to the plastic region, I need to increase my force, but at a smaller rate. Okay, so if you want delta F, let's say if I consider a certain delta strain, as I progress for a certain delta strain, delta F of increase will be smaller. While if you consider in the elastic region, for example, the same delta strain, you will need to increase much more your force. Okay, so it's not the force that is decreasing, but the rate of variation of the force with the strain. Okay, so for a certain delta gamma, you will need much higher delta F in the elastic region compared to the plastic region. And as you progress in the plastic region, for a certain deformation value, okay, you will need to increase your force, but by a smaller amount. This is the idea, but your force is always increasing.
اوكي دكتور، وبريتل ماتيريال فينا نعمل لهم compression test بس ما فينا نعمل لهم tensile test، انه hard to do tensile test، صح؟
Yeah, exactly. Yes.
Okay, thank you.
Any other question on this? Okay.
سوري دكتور، بس في شغلة ما فهمتها. البريتل ماتيريال فينا نعمل له shear stress, like shear test.
Yes, you can do a shear test, no problem. هو عادة بيعذب بالتنسايل test. Okay, so يعني because أول شيء عادة we do the tensile test when we have a plastic region. يعني هون أصلا elastic region is very limited وهو it will undergo failure if you want for very small values of strain. So sometimes it's complex to measure these values in case of a brittle material. So we prefer, for more accurate results, we prefer to do the test as bending test.
Okay, thank you.
Welcome. Okay. Another property that is very important for materials is hardness. Okay, and we can define hardness as the resistance to permanent indentation, okay, or permanent deformation. So we'll see here different tests that can allows us to measure hardness. So good hardness generally means that material is resistant to scratching and wear. Most tooling used in manufacturing must be hard for scratch and wear resistance. So all tools, tools used to be able to have a longer lifetime should have a high hardness because they will be under very high forces and stresses. And if they don't have high mechanical properties and high hardness, they will not be able to have a long lifetime, and we should change them continuously. So hardness is very important for the tools used, but it is challenging if the material we want to deform is hard, because harder the material, the deformation of it will be more complex. Okay. So hardness tests are commonly used for assessing material properties because they are quick and convenient. We have a lot of types of tests that can be used to measure hardness, and we have different scales that we'll introduce together in this session. So the most well-known tests are the Brinell and Rockwell tests. We have also other test methods that are available, such as Vickers, Knoop, but you are not responsible of these tests. We'll just concentrate on the most known one, which are Brinell and Rockwell tests. Now, what is the idea of these tests? So as we said, hardness is opposition to indentation, which is a certain permanent deformation caused when you have two materials in contact with each other. So let us say you have a specimen and you want to test its hardness. One way will be to do the following. You can bring a certain ball or sphere, okay, and of large mass, and you apply a force, a compressive force on the ball. If the force is very large and the mass of the ball also is large, this will cause like here a deformation of the specimen. Okay, and larger the hardness of the specimen, lower will be, if you want, this deformation. So when you remove the ball and you look at your specimen, you will observe a certain indentation, and it will be of a circular shape. So imagine that when you remove the ball, you are looking at the top, you will see like a hole of the form of cross-sectional area is a circle, and higher the hardness, lower will be the diameter of indentation. Okay, so we say that the idea here will be to use a ball. Now for the mass of the ball, it can be variable. Okay, and the hardness will be related to the value of the force. So what we do in general, we define, you have a catalog when you perform such tasks that will tell you that if the force is the force can be 500, 1,500, or 3,000. So larger the hardness of your material, you should use larger values of your weight. Okay. Look, when they give you the force in kilogram, all you have to do to convert it to Newton, okay, is to multiply by G. So it's true that they express it in kilogram, but this can give you the Newton value by just multiplying by G. So when we say a force, a load of 500 kilograms, this is equivalent to 5,000 Newton. Okay. Now, under the effect of this force applied, we'll have, as we said, after we remove the ball, we'll have a certain permanent indentation in the specimen. Now, the diameter of this indentation can be a characteristic of the hardness. So as we said, smaller is this diameter, larger will be the hardness. Okay, and we have like scales. One is called Brinell. We'll do together problems on this. We'll see what are the formulas that are used to determine the hardness function of these parameters, which are the force applied, the diameter of the ball, and the corresponding diameter of indentation. Now, another type of test is the Rockwell hardness test. So in this test, the concept is the same, but if you want, the type of deformation is different. So here we are considering that deformation is proportional to the penetration distance. So you have a tool and it has an end of conical shape. Now this conical shape, the indenter, is positioned on the specimen initially, and we then apply a load on it. Okay. Now, here the idea is that we apply first a small force and then we increase it. And we measure, due to this delta F, due to this variation in force applied, what will be the penetration distance of the tool in the specimen. And of course, also here, larger is D, smaller will be the hardness, because harder the material is, it will oppose any permanent deformation in the specimen. Okay, we have different scales for the previous test and Rockwell test, and each one is characterized by a certain formula. We will develop next time together these formulas, and we'll go over them, and we'll do some problems to practice on how we can determine hardness using the parameters of the test. So here we'll relate the forces applied to the value of D to a hardness on a different scale. So hardness, if you want, always need to be defined according to a scale. It's not like mass, and when I say 10 kilogram, I directly, if you want, understand what it is. And I have different scales for hardness. Now, other properties that are important is the effect of temperature on the behavior of the materials. Okay, so we have already studied tensile test, compressive test, shears tests, but we should pay attention that these plots are performed under certain conditions. So whenever they give you a plot, they should tell you what were the conditions under which the test was applied. Because if you change the condition, you might have a complete change in the behavior. Okay, so for example, here we can see how the temperature can affect the strength and ductility of a material. First, if you observe your curve, you have always increasing the temperature will reduce the strength, but will increase the ductility. Okay, so here we should always do a compromise if you want to decide what properties we want to have. So of course, when you want to deform, increasing the ductility or the percentage of elongation is very important, because it will lead to lower forces applied to perform your deformation, and this will save energy. On the other hand, your final product should be characterized by certain mechanical properties, and the strength of a material is important. So we should do a compromise between the facility of deformation. Okay, so we should try to have an easy deformation to not have large forces, but at the same time we should have final properties for the materials that are acceptable. So it depends on your application. What are your desired final mechanical properties? This will allow you to decide on which temperature you can use to perform your deformations. Now we can see here the effect of temperature on hardness. So as we said, temperature will increase ductility, but will reduce strength and will reduce hardness also. Now, some materials are resistant to decrease of hardness with temperature. And this can be done by appropriate combinations of materials. Sometimes this is why we form alloys. Okay, formation of alloys will allow you to reach good mechanical properties even at high temperatures. So for example, here, if we compare several materials, these are we are comparing different types of steels. Okay, and we know that one of the material used a lot in manufacturing is steel with a certain carbon content. Okay, and if we play with the carbon content, we can change the mechanical properties. So from here, the importance of alloys and how to decide on percentages used. This depends. So we'll do combinations. Let's say we introduce different proportion of carbons to steel, and we can test these mixtures and determine which one is convenient for our application. So for example, here they are comparing low carbon steel performance. So we are changing the temperature and looking at the variation of hardness. We are also observing we are increasing now the percentage of carbon, and we are seeing that as we increase the percentage of carbon, then the hardness will increase. And then even if we increase the temperature, we can still have a certain acceptable hardness. Now, you can have different alloys. Okay, you can implement other materials to your alloy, to your mixture, and you can see how this can affect hardness. Now, one of the most resistant materials to hardness decrease with temperature is ceramic. So in case you need to maintain a very large hardness for your final product, and you need to increase temperature to have better ductility, ceramic can be a good choice, because even at very large temperature, it will maintain a high hardness. Okay, so again, it depends on your final goal. What is the final mechanical properties desired? Based on this, you will decide which material you will use.
دكتور بس سيراميك مش هن بريتل اصلا.
انتبهوا على شغله، ما خص البريتل بالهاردنس. في يكون ماتيريال هارد وبريتل. بريتل ما اصلا نحن شفنا انه البريتل له علاقه بالدكتيليتي. بريتل ماتيريال is not ductile enough but it's hard, it might be very hard.
بعرف
اوكي
دكتور، ما هيك قصدي، بس انت قلت انه فينا نعوز سيراميك انه يكون عندنا تمبريتشر عالي to have ductility و hardness بذات الوقت، بس
yes
السيراميك
look
هن اساسا
no
بريتل.
هي الايديا look الايديا انت مش كل يعني انت في manufacturing processes اوكي that will not require يعني بقلب هول البروسيسز ما you are not going to very large tension values اوكي. يعني مش كل الديفورميشن بيعوزوا تكون اذا بدك انه انا اروح على البلاستيك ريجن بالتنسايل تيست because it depends on the stresses that you are undergoing بالdeformation. يعني اذا انت عندك تيست بدك يمكن high very large shear values مش to go to very large tensile stresses, you have the option of ceramic because it will allow you to keep large hardness. اوكي
اوكي
يعني مش على طول البريتل ماتيريالز في لهم ابلكيشنز كمان بالمانيفاكتشرينج. بس اذا كان عندي manufacturing process that requires the application of large tensile stresses ساعتها ما بستعمل brittle material. But for other applications يمكن shear او عندي deformation by shear I can use ceramic because it's characterized by large hardness.
Thank you doctor.
Welcome. Now, concerning, we have already introduced the concept of recrystallization in metals, and now we'll see what is this phenomenon. Okay, so we have that most metal will have the strain hardening behavior at room temperature according to the flow curve. So if you remember when we introduced different behaviors of materials, we said that one possible behavior is 1 second. Look, I will open a new session to continue, okay? Yeah.